So now we move on to collisions in two dimensions, and what we got is basically we're sort of in the same area as we were before with collisions in one dimension. The only thing is we still have perfect inelastic collisions where you've got two objects that will join together and become, for better or worse, one object and go off in some direction. Or you've got normal inelastic or perfect elastic where you have two balls or two objects that may come in and hit each other and then become two objects that go zipping away from each other, or maybe they go off in one direction at different speeds, or somehow, some way, some iteration of that. But again, two objects into one object versus two objects into two objects. And that's really the delineation for what types of collisions we're dealing with. The issue with two dimensions is now that we are in fact dealing with two dimensions. And I'm still going to be making my little, the chart that, I wouldn't even call it a chart, but I'll still make my graphic where we're dealing with stuff before the collision and stuff after the collision. But the fact that we're dealing in two dimensions now means we're going to have object 1 and object 2, and what it's doing in the x and y dimensions, or what they're doing in the x dimension and y dimension before the collision, and what they're doing in the x dimension and the y dimension after the collision. So you're going to see a lot of this kind of chart where you've got one object and then the other object, what they're doing in the x and what they're doing in the y, and then what their total momentum is. And I think this is the big thing that everybody needs to remember. What goes on in these two boxes is momentum. Not velocity, not mass, not anything else. Momentum. Because if we go back to the very beginning of this whole thing, momentum is what gets conserved in collisions. So remember when I did this. Momentum is conserved. Momentum is conserved. And momentum is conserved. These three collisions, what we're dealing with whenever we're dealing with anything that has a collision, we're dealing with momentum being conserved. Okay, so whatever goes on in here, inside of these charts, is always going to be a factor of momentum. And I think the best way to really deal with this is just look at the two problems that you have on, the two problems that we have left on the sheet, and they're kind of quintessential for whatever else I can give you. So let's go through them. Number 6 on the sheet that I gave you is that a 10 kilogram watermelon is hurled to the south with a velocity of 20 meters per second. So we've got a watermelon, WM, I'm just going to probably change this to W later on, where the velocity is 20 meters per second, and its mass is 10 kigs, and it's going towards a baby hippopotamus that is running this way, so we're going to have an H for hippo, and its velocity is 5 meters per second, and its mass is 100 kilograms. So you've got this animal running this way, and you've got this watermelon being thrown this way, and hopefully in the middle here, the hungry hippo is going to eat the watermelon. And what kind of collision that is what's going to determine how we really handle this problem. Well, if the watermelon goes into the hippo's mouth, and the hippo eats the watermelon, the hippo is going to gain 10 kilograms of mass, and this is going to be a perfectly inelastic collision. So that's the first thing we need to know. And the thought is that eventually that object, or the watermelon and the hippo, are going to go off somewhere in this general direction. I don't know what I don't know exactly which direction, but I'm assuming if we're dealing with a vector that's going down and a vector that's going to the right, you're going to end up with another vector, a resultant vector, that's going to go down and to the right. So we should probably look at this just like we've looked at the other ones, before and after. And we need to remember that whatever goes on here is going to be momentums. So let's go with P of the watermelon and P of the hippo before, and P of the watermelon slash hippo after. Again, because these two sort of join together and we're going to make a new object. That's the watermelon and hippo put together. And we should look at the total momentum before and the total momentum after. Okay? So I think that's a pretty good chart. And what we need to remember, though, is that we're in 2 dimensions. So we're going to have to deal with what's happening in the x and y dimensions, just like we did earlier in the year, because these are vectors. So for the watermelon, we're dealing with a velocity of negative 20 meters per second because we're going south, we're going down. So the v is actually negative 20, and the mass is 10. So 20 times 10 gives us negative, and I'm actually going to scoot this down a little bit. It's going to give us a, oh boy, maybe we'll just do this, move that up there. Good. There's a little more real estate to work in. Give us some momentums. Excellent. Negative 20 times 10 is going to be negative 200. And I'm putting that in the y. And the x, because it's just going straight down, is going to be 0. And the momentum of the hippo is 5 times 100, or positive 500 kilogram meters per second, and nothing in the y. So negative 200 kilogram meters per second because it's going down, and positive 500 kilogram meters per second in the x because it's going to the right. So I hope that makes sense. And what we're going to do is we're going to figure out the total. So 500 plus 0 is still 500. And negative 200 plus 0 is still negative 200. So the total momentum before the collision is going to be 500 in the x and negative 200 in the y. Well, that's nice. What about after the collision? Because that's what we want to know. What happens to this after he catches the watermelon? Well, the total's not going to change. And that's sort of the entire point about conservation of momentum. If you had 500 kilogram meters per second in the x dimension before the collision, you're going to have 500 kilogram meters per second in the x dimension after the collision. And if you had negative 200 in the y dimension, you're still going to have negative 200 in the y dimension after. So when you're dealing with a perfect inelastic collision, the beauty of this is that you've got one object after the collision and you've got 2 momentums, so that one object is going to display both momentums. It's going to display both the positive 500 in the x and it's going to display the negative 200 in the y. And during class, I kind of get a little jumbled up, so I'm going to say, okay, fine. Here I've got a little more real estate, and I'm going to make this make hopefully a little bit more sense. The collision happens here. The objects join here. And they're going to display a motion that is 500 kilogram meters per second to the right, as well as 200 kilogram meters per second down. And what that's going to do is that's going to give us I'm going to get this nice, a resultant momentum that is something. And we can figure out what that something is with Pythagorean theorem. A squared plus b squared equals c squared. And if you do it out correctly, you should end up with 500 and 200, and then you take the square root of both of those. You should get 538 kilogram meters per second. Now the trick here is this is a momentum, this is a momentum, and this is a momentum. I don't care about momentum. I care about velocity. So remember that this 538 equals mv. And we're solving for the velocity because we know the m. Remember that the hippo had a mass of 100 kilograms. And it ate a watermelon that had a mass of 10 kilograms. So now my hippo and watermelon's new mass is 110 kilograms and its new velocity. So 538 equals 110 v. 538 kilogram meters per second equals 110 kilograms times the velocity. Divide both sides by 110. And you should get a velocity that is 5.13 meters per second. And then I'm going to, because we're looking for a velocity, we need a direction. And we're going to have to do, come back up here, and our angle is this thing. So this is my opposite, this is my adjacent, and this is my hypotenuse. I would say use the inverse tan function of opposite, 200. And remember, this is just a direction, so we don't really need to worry about it when we're talking about sides of a triangle. So I'm going to throw away the negative, over 500, and you should end up with 22 degrees, what we would call south of east. So your new velocity for your hippopotamus would be 5.13 meters per second at 22 degrees south of east. So I hope that helps. And this is just, again, one two-dimensional type of problem where you have a perfect inelastic collision. Okay? And because it's perfect inelastic, I am technically telling you something about what happens after the collision. I'm telling you the mass that all of this momentum has to count for. So I hope that makes sense, and please feel free to pause it if there was anything confusing, but I think this is a little bit more linear than what I'm able to do at school on board. The next problem is a little tougher, and I'm going to end it with this, and hopefully you'll be able to sort of watch this and sort of figure out what actually happens in any of these collisions, because we're basically dealing with the same thing. We're talking about, now this time, 100 kilogram bumper car that's traveling north with a velocity of 2 meters per second when it gets hit by a 75 kilogram bumper car traveling east with a velocity of 2 meters per second. So they're both going the same speed, one of them is more massive. I'm also telling you that the 75 kilogram car bounces off with a velocity of 1.88 meters per second at a 45 degree angle north of east. They bounce off each other. So we're not dealing with a perfect inelastic collision. We are dealing with either a perfect elastic or a normal inelastic. Because we're dealing with bumper cars, probably in the real world, it's probably not going to be a perfect elastic either. It's going to be a normal inelastic collision. But potatoes, it really doesn't matter because we solve for perfect elastic and normal inelastic the same way. I want to know what the other car does. All right, fine. So, let's look at what's going on before the collision and let's look at what's happening after. Before the collision, we've got, I'm just going to call them what they are. The 100 kilogram bumper car and the 75 kilogram bumper car. 100 kilogram, 75 kilogram, and notice they don't join together. Here, they did. Here, they don't. So we're going to end up with a total momentum for both of these. Total. And remember that the conservation of momentum states that the total here has to equal the total here. So, what's the momentums? We care about x and y because I told you these are two-dimensional. So let's draw this out. I guess that's a good way to do it. 100 kilogram bumper car is traveling north. Boom. 100, and its velocity is 2 meters per second. And it is hit by another bumper car that is 75 kigs, traveling 2 meters per second to the east. Okay? So I've got one going this way and one going that way. The 100 kilogram, 100 times 2 is 200. That's its momentum. 75 times 2 is 150. That's its momentum. And I guess to start out with, we should say who's going in the x dimension, who's going in the y dimension. Well, the 100 is going in the y. Positive 200 kilogram meters per second. And it's not doing anything in the x. The 75 kilograms seems to be doing 150 kilogram meters per second in the x and nothing in the y. So far, so good. So now I've got my before the collision scenario, and I really don't care about this anymore. And you'll see why in a second. My total momentum before the collision is 150 in the x and 200 in the y. And that's going to carry over. So whatever happens after this collision, I'm still going to have 150 in the x and 200 in the y. I hope that makes sense. And it's only because what happens before also has to happen after. Now remember the fact that I gave you the 75 kilogram bumper car after the collision? Well, that means I'm going to be able to write something here, and I'm going to be able to write something here. Because I tell you, the 75 kilogram bumper car does something after the collision. So I'm going to have numbers to fit after. What are those numbers? Well, I've got a velocity, 75 times 1.88 meters per second, 45 degrees north of east. So I can't put this in the x, and I can't put this in the y. I have to resolve this to go in somewhere in the x, and some of it's going to go in the y as well. But I'm telling you that we have a something at 45 degrees north of east. Okay? And we actually give you a mass and a velocity, so I can tell you what that momentum is. And if I know what that momentum is, and I know the angle, I can also figure out what the x and the y components of that momentum are. So P equals mv, 75 times 1.88 should be, I'm going to have to do this on my calculator. Oh, Tom Brady, 4 games. Great. 75 times 1.88. 141 kilogram meters per second. Okay. So if this hypotenuse is 141, I should be able to figure out what the adjacent and the opposite sides are. And then since a 45-degree angle, I can figure out one and know the other because they're the same. And I would do that because I have the hypotenuse here. And I probably would use sine. Sine of 45 equals the opposite. So I'll figure out this guy over 141. So multiply both sides, 141 times sine 45. As long as you are in degrees, you should end up with 99.7 there and 99.7 there. Again, 45 degrees, this side equals this side. So now I can get rid of my little squiggly lines here and here. Why can I get rid of my squiggly lines? Because now I know that the 75 kilogram car after the collision is going 99.7 kilogram meters per second in the x and positive 99.7 kilogram meters per second in the y. These two things become these two things. I hope that makes sense. I have total momentum too. So now I've got what one car is doing. I have what the total's got to be. I got to figure out what the other car is doing. Well, if I'm totaling up to 150 and I've already got 99.7 accounted for, this guy's going to be, what, 50.3? Because 99.7 plus 50.3 equals 150. And this guy should be 100.3 because 99.7 plus 100.3 equals 200. All I did was subtract this from this to get this, and I subtracted this from this to get this. So now I know what my other car is doing. I hope you hear that. My dog is having a nice drink right now. This can go away for the time being. Okay, so now my 100 kilogram car is going to have a momentum in the x dimension of 50.3 kilogram meters per second and a momentum in the y dimension of 100.3 kilogram meters per second. Obviously this is not to scale. Let's try and make it a little more to scale. It's better. But we want to know what the hypotenuse is going to be. What is this side going to be? Well, to do that, it's actually not that hard. A squared plus b squared equals c squared, as long as we remember these are momentums. So 50.3 and 100.3 will give you a pretty big number. 50.3 squared plus 100.3 squared will give you a big number. And then if you take the square root of that, you should get 112-ish meters per second. I'm sorry, kilogram meters per second. Okay? So we have a momentum here. I hope that makes sense. 112 kilogram meters per second. But we don't have a velocity. we have the momentum. So because P equals mv, we know the momentum, 112 equals m, but we know the mass is 100 times the velocity. So 112 over 100 to divide this and solve for v. 112 divided by 100, it's going to be 1.12 meters per second. That's your velocity. But I also want to know the angle. So we know the second car is going to go at 1.12 meters per second at some angle. We've got to figure out what that is. Again, I would say inverse tan of the opposite side, 100.3, over the adjacent side, 50.3, and we should end up with an angle of 63 degrees. Okay, so anytime you deal, so there you go. There's your final answer, 63 degrees north of east, technically, north of east. But if you just draw a triangle, I'll be able to figure out what you're using for the angle. So we know one car is going 1.88 meters per second, and the other car is going 1.12 meters per second at 63 degrees north of east. So it's almost like you've got this car, and it hits this car, and then you're going to have one car go at 45 degrees, and you're going to have another car is going to go 63 degrees, like that way. So these two will hit. One will go that way at 45 degrees. This one, the other car would go this way at 63 degrees, 1.33 meters per second, 1.12 meters per second. Okay, so I hope that kind of makes sense, and that's how all of these work. I have to give you a momentum of everybody before the collision, and then I have to give you a momentum of at least one of the things after the collision. And once you break that up into x and y components, you can figure out what the momentum of the other one is in the x and y, and then you can go ahead and figure out what it's actually doing and figuring out its velocity. So I hope that helps. I know it's only 2 problems, but if you can use these for the rest, to go over these, and then tomorrow in class, hopefully, you'll be able to work on some other problems in class. You should be ready for the exam coming up, whenever it's going to be, either block day or Friday. Alrighty, I hope this helped. Take care. I'll see you tomorrow.